Okay, looking at the free response questions of the practice test, I'm going to go ahead and do them all in one video since there's only one that requires a calculator. The first one, you have two walkers, Alex and Bob, that are walking. Let's see, they start at the same time from the same place and travel in the same direction. You have two functions that give you the velocity of each walker. You have A prime is Alex's velocity, B prime is Bob's velocity. They're measured in miles per minute. Always pay attention to units. Let's see, time starts at 0 and they walk until they have the same velocity. Now, since this is a calculator problem, I have already in my calculator stored my A prime for F1 and I've stored my B prime for F2. And that's what I'll do at the very beginning. I've gone ahead and adjusted my window so that my x's on my graph would be greater than 0. And it says, at what time do they stop walking? Well, it does tell you that they stop walking when they have the same velocity. So when their velocities are equal, they will stop walking. So A is going to be pretty easy. The thing is, you must write down the equation. So we're going to stop walking when those two equations, A prime is equal to B prime, when they have the same velocity. If you want to write the actual equation, you can, not necessary, but I will. E to the t minus 1. And the reason you didn't have to write the actual equations as opposed to the names of them, like A prime and B prime, is because this is a calculator equation. You're not going to have to solve this by hand. And let's see, there is the graph. You can see each one of them. And these two graphs are equal at the origin, which makes sense because it said they started at the same time with the same velocity at the same place. But this intersection right here will be when they stop walking. So I'll go menu, analyze, 0, oh, geez, not 0. I need to find the intersection. See, let's get out of there. Menu, analyze, intersection, and then I'll drag across, and they intersect at 1.6094. I will likely need that answer later on, so I'm going to click on that value, Control, Store, and I'll choose to store that for A. So we get 1.609, and remember, all answers must be accurate to the third decimal. So they stop walking at t equals 1.609. There's my answer to part A. And then just make a little note to myself, I have stored that in my calculator for A in case I need to retrieve it later. Let's see. B, at the time they stopped walking, which walker has traveled further and how much further has he traveled? So now we need the total distance traveled. Well, total distance is going to be the antiderivative of velocity. So my total distance for walker B, Bob, will have traveled the antiderivative of, let's do Alex. Let's go A first, right? Whatever. So Alex would be the antiderivative of 1 minus e to the negative t dt. And we know that he stopped walking at 1.609, so I'm going to measure his velocity from 0 to 1.609. And this is why I stored the value. I'll throw that in the calculator. And while I'm at it, I'm going to go ahead and set up Bob's antiderivative. His velocity was 0.2 times e to the t plus minus 1. Whoops, not t to the t. Minus 1 dt. And that again is going to be measured from 0 to 1.609. Now looking at the graphs, I can tell that F1, which is Alex, had a higher velocity. So I can look at the graph and tell that Alex is going to walk further. Now we need to figure out how much further, and we'll do that with the antiderivatives. So I'll go back to my calculate screen. I will do Shift plus for the antiderivative. I'm going to go from 0 to, and I stored that point for A. And Alex was F1 of x, go on, dx. I'm going to go ahead and hit Control Enter to force the decimal, and we get 0.809. So Alex traveled 0.809. Always include units. This was measured in miles per minute. So the distance traveled would be in miles. Bob. Oh, by the way, I'm going to store that answer because I'm going to need to use that later. So I'm going to Control Store Previous Answer for B. Now I need to find the distance that Bob traveled. Same antiderivative, except we're going to use F2. So I'm actually going to go up here, highlight, hit enter, and then just go back and change the 1 to a 2. There we go. Control enter. And Bob traveled 0.478. Again, I'm going to store that, and I'll just walk through my alphabet, store that for C, so we get 0.478 miles for Bob. And then it says how much further has he traveled. So I would say that Alex traveled. And then to find the distance, I'm going to take this one up here was stored for B. Always make notes to yourself. That was B. This is stored for C. And so I need to figure out what B minus C is. So I'll just do B minus C. And he traveled 0.331 miles further. All right, so there is the answer to question B. Shrink that up, give me a little bit more room here. All right, at the time, oh, nope. Number C, write an expression that represents the distance between the walkers at any time t. So if you want to find the distance between the two walkers, what we essentially did was, right here, was we did the antiderivative of Alex minus the antiderivative of Bob. So the distance between them for any time t, I'll change to green. So the distance between them, well, it's going to be the antiderivative because I want total distance. But we know that Alex traveled further, and by looking at the graphs, we can tell that, is the bell ringing? Students aren't even here yet. We know that Alex is ahead of Bob the entire time. He had a faster velocity, a higher velocity the entire trip. So I'm going to make sure I put Alex first, and the total distance is going to be Alex, which was a prime of t, the antiderivative of a prime of t, minus the antiderivative of b prime of t, dt. And then it says an expression that represents the distance between the walkers for any positive value of t. And we know they stopped walking at t equals 1.609. So really, it's going to be for 0 less than t less than 1.609. But let's say I wanted the distance between them at time 0.5. Well, then I would measure this integral from 0 to 0.5. If I wanted the distance between them at time 1, then I'll do the area from 0 to 1. At 0.1, I'll do the area from 0 to 0.1. So really my variable and what's changing is my upper limit of integration. So my distance between them at any time t is going to be the antiderivative from 0 to t. Instead of 0 to 1, it's going to be 0 to t of this. Now this is not perfectly correct. I'm going to make one more subtle change. And that's almost there. What I need to fix now is we have a conflict, what I call a conflict of variables. You are not allowed to have the same variable for a limit of integration as you do for the variable inside the integral. So I will fix that by simply erasing these t's right here and calling them anything else you want. I'm just going to go simple and call it x. And there we finally have our expression that gives the distance between them. So that upper limit changes depending on the time value. Okay, and finally, number D. At what time is the distance between them the greatest? Ooh! Anytime something references the greatest or the least or the most or the smallest or anything like that, we know we're going to need critical numbers, and we want the greatest distance. So I'm going to need the critical numbers of distance. Well, that means I'm going to need to set what I call d prime of t equal to 0. And d prime of t, well, this is going to be easy because d prime, we're simply going to take our, I'm not going to worry about that. We're going to take our t and we plug it in for the x's. So d prime of t is going to be a prime of t minus b prime of t and we'll set that equal to 0. And we'll solve that equation, and that's going to give us our critical numbers. Well, that's going to be whenever a prime of t is equal to b prime of t. And this is kind of a silly question. I kind of hesitated there a second ago because I realized that this was kind of a goofy question. Well, this equation, a prime equals b prime, we have already answered. And that's what we answered in part A. So the critical number is going to be t equals 1.609. And we actually stored that in part A, and we actually have that still stored for A. And the reason this is a silly question, again, going back to the graphs, if Alex has a higher velocity the entire trip until this point where they stop walking, but if he has a higher velocity, then he's walking faster and faster, and the lead is growing the entire time until they stop walking. So by analyzing the graph, I know that this point in time is going to be where they intersect. Now, the thing is, we have to show sufficient work, and it does say show the work that leads to your conclusion. We are on a closed interval. We're going from 0 to 1.609, so I'm actually going to use the extreme value theorem, where you test the distance at the endpoints, which was 0, and my distance at 1.609, and you test critical numbers. So we test ends, endpoints, and critical numbers. The good thing here is the only critical number we got was also an endpoint, so I don't have to worry about it. And I've actually already done this work. My distance between them at time 0 is 0, because they tell you that they start at the same time, at the same place, and travel in the same direction. And then the distance between them at 1.609 was actually the same question as B. That's going to be 0.331. And then the question, make sure you answer the question, says at what time is the distance the greatest? So the distance is greatest at time equals 1.609. So that was kind of a dumb question because it essentially repeats questions A and B, but that's fine. All right, so that one took longer than I thought. I hope I don't spend 12 minutes per free response question. As a matter of fact, I'm going to go ahead and stop there, and I'm going to do another video for the non-calculator questions.